Section 6.8 is one of the most crucial sections that's never going to go away. Not in this class, not in 5C, not in 55, not in any science class, any upper division engineering class, or computer science class. This is all over the place. Something you really want to get out of the way. I'm going to break that into two sections, two lessons. First lesson I'm going to focus on, well, let's get things out of the way. 1 over 0. Remember, I'm talking about a limit, you guys. 1 over a very small number is either plus or minus infinity. If you're approaching 0 from the right, it's positive infinity. If you're approaching 0 from the left, it's negative infinity. And 1 over infinity plus or minus is 0. You need to get that out of the way from now on. I'll show you a couple of examples to really show you how we've been avoiding this all along. Really. So, if I take infinity plus a, where a is any number, that's infinity. If I take infinity plus infinity, anytime I say infinity, I'm talking about a very large number. You add two large numbers, you get a larger number. If you take a very large number multiplied by 5, that's a large number. If you take a very large number and multiply it by -1, that becomes a very small number. I don't mean by a very small number like 0.001. No, that's not small. -1,000 is way smaller than that. So those cases we dealt with somewhat in 5A. And I'm going to show you an example on why this works. 1 over 0 is infinity. So in algebra, 1 over x minus 1 equals 1 over x minus 1. We agree? What happened if I added 1 to the one of the sides? Couldn't that not equal anymore? When you got this in algebra, you find the LCD and you cleared the LCD. The LCD was x minus 1. So this is missing nothing. This is missing nothing. And this is missing an x minus 1 top and bottom. Since this is an equation, you ignore the denominator. And those cancel out. And you get 1 equal x. And back in the days, you said, wait a minute. That's not in the domain. Well, why is that? Do you know why it's not in the domain? Because if you put 1 in there, you get 1 over 0 equal 1 over 0 plus 1. Infinity equal infinity plus 1. Guess what? Math solves it for you. Math did tell you that, you know what, the only way you could get those two quantities to equal if you make that infinity. Which is not allowed because we don't use infinity in algebra or with numbers, but that is the idea. So, those supposed to be straightforward. What's not straightforward, if I say, what's a very large number minus a very large number? Well, it depends which of those is larger. What is infinity times 0? A very large number times 0. Not sure. What is a very large number divided by a very large number? Unknown. What is 0 over 0? Also unknown. Now, the three values that we've been leaving out, 0 to the 0 in algebra all along has been undefined. Infinity raised to the 0 is always undefined. 1 raised to the infinity is always undefined. That's a tricky one. That's because of complex numbers. You really don't touch on those until you take Math 55. Well, to do all of these problems, we really need the famous L'Hopital's rule. It looks like hospital. It's pronounced L'Hopital. This is what L'Hopital discovered. L'Hopital stated, if you are taking the limit as x approaches a of f of x over g of x, and you get 0 over 0, I'm adding to it. I'm adding to the definition, or infinity over infinity. Then, the limit as x approaches a of f of x over g of x will equal the limit as x approaches a of f prime of x over g prime of x. And that turns out to be a lot more important than you think. Tell you a few things. Since we're dealing with infinity and zero, the fastest growing function that we have in this book is factorial. The second fastest function is exponential. Polynomials come after, radicals, and the slowest growing functions are logs. And it's not a surprise that to undo a very fast function, the inverse would be, sorry about that, that was my phone. The inverse would be a log, which is a very slow function. To undo a polynomial, you use a radical, those are inverses. And since up till now we can't undo an exponential, a factorial, that has no inverse. And another thing to remind you of, the shortcut for a limit. If you take the limit as x approaches a of f of x, you substitute the value in under certain conditions. I'll say when those are. You throw a in. If you get a number, you're done. If you get a number over 0, initially we used to say does not exist. Now we want to go for positive infinity or negative infinity. And if you get a number 0 over 0, or in our case infinity over infinity, we manipulate the problem. Of course, f must be what? A radical, a log, an exponential, trig where they're defined, rational where they're defined, polynomials, right? And the list goes on. Absolute value is not allowed like usual, and all of these other things. So I want to play with few things. We memorized back in the days that the limit as x approaches 0 of sine of theta over theta equals 0. Well, throw 0 in. Isn't that 0 over 0? Every time you use L'Hopital, you put an h on that equal for me to know what you did. That's the limit as x approaches 0. And this is derivative of the top, derivative, it's not a quotient rule. Derivative of sine is cosine. Derivative of x is 1. If you throw 0 in, isn't that cosine of 0, which is 1? So I don't have to memorize many things now. Well, how about this problem? I know how to do this. I know I could factor the bottom, and you could do that if you wish. It says find the limit, use L'Hopital's rule when appropriate. If there is a more elementary method, consider using it, not a problem. If you throw 3 in, don't you get 0 over 0? Again, you could factor and go from there. I really don't mind, that's fine. Or you could use L'Hopital since it applies. What's the derivative of x minus, that's a 1. What's the derivative of x squared minus 9, 2x? Throw the 3 in, that's 1 over 6. You want to factor the top and the bottom and cancel out, you could do that too. Same deal here. If you throw a negative 2 in, you get negative 8 plus 8, which is a 0 over 0. Now, this is, you're doing this to make sure that you're not running into this case. You can only use L'Hopital if you happen to see 0 over 0 or infinity over infinity. If you don't see those two, you can't use L'Hopital. Well, I'm going to use L'Hopital for practice. I know I could factor the top and the bottom. Limit as x approaches negative 2. That's 3x squared over 1. Throw the negative 2 in. Negative 2 squared is 4 times 3. That's a 12. How about here? This gave us a hard time last class. Tan of 0 is 0. Sine of 0 is 0. Guess what? By L'Hopital, limit as x approaches 0. That is the tangent, that's secant squared of 3x times 3. And that is the cosine of 2x times 3. If you throw 0 in, that's a 1 times 3 over 1. I'm sorry, that's a 2, right? You guys say something. And that turns out to be 3/2. No need to go with as we did back in section 3.4 and do all of these manipulations. Throw a pi in there, what do you get? Well, I'll get 1 minus 1 over 1 minus a negative 1. I'll get 0 over 2, which is 0. If you use L'Hopital on number 18, and 18 was on the test, I'll give you a 0 for that problem. If you use L'Hopital when it doesn't apply, that's why I insist on you showing me this. How about here? t equals 0. a to the 0 is 1 minus 1 over 0. That is 0 over 0. I could use L'Hopital. That's the limit as t approaches 0. Denominator is a 1. The top, 8 to the t times natural log of 8. 5 to the t natural log of 5. Throw 0 in. 8 to the 0 is 1. You get natural log of 8 minus natural log of 5. You could leave it like that, or you could say that's natural log of 8/5. Whatever makes you happy. Now, L'Hopital could be applied multiple times, like number 40. If I put a 0 in there, I'll get 1 minus 1 minus 0, which is 0. And I'll get 1 minus 0 minus 0, which is 0. By L'Hopital, that's the limit as x approaches 0. Derivative of e to the x is e to the x plus e to the minus x minus 2 over 1 minus cosine of x. Put a 0 in, I'll get 1 plus 1 minus 2, that's 0. 1 minus 1 is 0. If I apply L'Hopital again, I put the h again. I use h every time I use L'Hopital. Derivative of e to the x minus e to the minus x over, this will be the sine of x. And if I put in a 0, I'll get 1 minus 1 over 0. L'Hopital 3 times. No problem. That is e to the x plus e to the minus x divided by cosine of x. Put a 0 in, you get 1 plus 1, which is 2 over 1, which is a 2. If you make a table and use that, there it is. You will get a 2. Exciting, wouldn't you say? So, now I'm going to deal with the case of infinity times 0. And look how this works. I'm going to use algebra and say, if you are given f times g, I could say that is f, instead of multiplying, I could divide by 1 over g. So I could say that's f over 1 over g. Or I could say that is g divided by 1 over f, which is g over 1 over f. So here, if I multiply by the reciprocal, I'll get f times g, and here, if I multiply by the reciprocal, I'll get f times g. The idea is that if I'm looking at a problem and I see infinity times 0, if I can manipulate that and write that algebraically as infinity over 1 over 0, that would be infinity over, and since that's 1 over 0, that's infinity, I could use L'Hopital, or I could say that's 0 over 1 over infinity, and we agreed that 1 over infinity is 0, and then I could use L'Hopital. And that applies to the next 4 problems. I think 4. Yeah. Well, here, if I take the limit as x approaches infinity, radical will approach infinity. This is exponential decay, that's 0. So I have a couple of options. Either I say this is the limit as x approaches infinity of radical x over e to the x over 2. Or I say this is the limit as x approaches infinity of e to the negative x over 2 over 1 over radical x. It doesn't matter. I'm going to choose this because it looks nicer and easier. So now that I'm looking at this, I notice that this is infinity over infinity. I would apply L'Hopital, and that would be the limit as x approaches infinity. Derivative of square root of x is 1 over twice square root of x over derivative of e to the x over 2 is e to the x over 2 times 1/2. If I clean this up, this is the limit as x approaches infinity. The 2's cancel out. That is 1 over radical x e to the x over 2. And as x approaches infinity, if the denominator is growing without bound, wouldn't that be 0? Because that's 1 over infinity. And there it is. That's how we do those. So the manipulation, the algebraic manipulation, is a must. Alright? Of course, the other way works as well, but one of those is normally easier than the other. If I look at this problem, limit as x approaches negative infinity, well, what do I notice? This is negative infinity. As x approaches negative infinity, this approaches 0. And natural log of 1 is 0. I'm going to manipulate. I have a good hint for you. The excellent hint. If you see a problem with an inverse trig function or a log, you never touch those. So you're really going to take the limit as x approaches negative infinity. A log or an inverse trig function, whether you're integrating or taking a limit, you never touch. If I want to take x over 1 and put it as a fraction, isn't that 1 over x? As x approaches negative infinity, this approaches 0. Natural log of 1 is 0. And 1 over negative infinity is 0. I could apply L'Hopital, limit as x approaches negative infinity. Derivative of natural log is 1 over the argument times derivative of negative 1 over x is 1 over x squared. Derivative of 1 over x is negative 1 over x squared. Those cancel out. I'm left with the limit as x approaches negative infinity of negative 1 over 1 minus 1 over x. That approaches 0. I'm left with a negative 1. There it is. Same deal here. Pi over 2. If you put a pi over 2 in there, cosine of pi over 2 is 0. Secant of pi over 2 is infinity. Well, this is an easy fix. That's the limit as x approaches pi over 2 from the left of cosine of x over cosine of 5x. And now I could say that's 0 over 0. That's the limit as x approaches pi over 2 from the left. Negative sine of x over negative sine of 5x times 5. And if you put pi over 2, that's going to be negative 1 over negative 1 times 5. That is a positive 1/5. All right? And one more, because I don't want to leave any stone unturned. The last problem is looking like this. If I put infinity, that is infinity times, and this is going to approach 0, sine of 0 is 0. I'm going to say this is the limit as x approaches infinity. And if I leave the sign out of it and move that to the bottom, isn't that x to the negative 3/2? Algebraic manipulation. Now, as x approaches infinity, right, this is 1 over infinity, that's 0, and that sine of 0 is 0. By losing L'Hopital, limit as x approaches infinity. Derivative of sine is the cosine of 1 over x times negative 1 over x squared. Derivative of x to the negative 3/2, bring the power down, subtract 1 from the power. This is the limit as x approaches infinity. And let's see how this works. This is actually positive 2/3 the cosine of 1 over x. What is 1 over x squared times 1 over x to the negative 5/2? Or say divided by 1 over x to the 5/2. Don't you multiply by the reciprocal? That's x to the 5/2 divided by x squared. That is square root of x. As x approaches infinity, this approaches 0. Cosine of 0 is 1. This will be 2/3, and this will approach infinity. And 2/3 times infinity is infinity. And the homework on this section is listed right there.